Okay, so we can start now, and good afternoon, everyone. Before we begin this panel of the World Quantum Day with the expert of professors and engineers who are going to present us in 20 minutes the nice panel questions and answers about the latest state of the art of quantum technology, I would like to briefly set the stage on what quantum technology really represents and why this moment in history is so important nowadays, and where our contribution in Open VQA through quantum computing, which I founded since 2023, is important for the global ecosystem and for the students and for the talents. So, short definitions about quantum mechanics. For those who are not knowing a lot of quantum, it's now the moment to know the definition of quantum mechanics. So, quantum mechanics is one of the most profound scientific revolutions ever discovered. It was born in the early 20th century through the work of great minds like Einstein, like Max Planck, Niels Bohr, Robert Heisenberg, Erwin Schrödinger, and of course many others who have revealed that at the microscopic scale, nature behaves, in fact, in a fundamentally different way than the classical physics predicts. So Albert Einstein himself played a paradoxical role in this story while he helped establish quantum theory through the photoelectric effect. As most of you know, he famously remained skeptical of its probabilistic interpretation, once he saying that the God does not play dice with the universe. But yet, despite this doubt of Einstein, the quantum world has proven to be one of the most accurate and successful theories in all science. So, since Feynman, he has established the prospect that saying that the quantum simulation is important and important through then the quantum computer nowadays has been doing. So, as I mentioned, Richard Feynman brought a transformative idea in the 1980s. He suggested that it's important to simulate the nature efficiently. So we would need computers that can operate according to the quantum laws themselves. This vision marked the birth of quantum computing. And here we are celebrating all together the World Quantum Day in 2026. You can imagine 1980s up to 2026, long so far away. And now we are ready to help each other to discuss and to make a panel in order to discuss. So why then later happens the witnessing of the vision becomes reality? Because from the John Bell's inequalities to David Deutsch's universal quantum computer to Peter Shor's, who has established the factoring of the algorithm Shor's factoring, and many other breakthrough to the quantum theory has evolved and evolved progressively over the decades of the year from a foundational mystery into a technological frontier. So nowadays, we have a lot of efforts from hardware engineers and from software engineers to make the quantum computer really ready to advance a lot of problems. So why now it's important? Nowadays, we are in the era we called it noisy intermediate scale quantum systems, where early quantum processors are already being built and tested over quantum hardware startups. At the same time, we have the artificial intelligence is playing a key role nowadays in the way how it can make high performance computing. It can help a lot to also faster the intelligence of designing the quantum processor unit, designing the NISQ devices into arriving into a fault-tolerant quantum computer, which is the changing big games nowadays in the market. And then the quantum algorithms through AI can converge into the best results. So this is the convergence nowadays. What's what making today unique? Quantum hardware is emerging. The algorithms like variational quantum algorithms, quantum phase estimations, quantum annealing are advancing a lot of effort since 2014. AI is accelerating discovery of many methods, and global investment is accelerating across the USA, across Europe, across the Middle East and Asia, and many others, and Australia, of course. So what's currently we have in the in the market. So quantum market is really huge. As you can see here in the figure, we have three pillars of focus in the quantum market. We have the quantum computing, we have the quantum communication, and the quantum sensing. So according to the reference there in 2025, it has been shown that the quantum computing increasing from $4 billion to $48 billion in 2030 is expecting to have investment from the private and the public as $48 billion according to the referee. And quantum communication, which is very important for the quantum defense as well, from $1.2 billion into $7.8 billion. And the quantum sensing to 2030 is expected to arrive to $4 billion over $0.5 billion from 2024. So this is huge. That means there are a lot of focus now in the investment. The market's increasing, and a lot of startups are really nowadays created in order to enter the games in the market through these three pillars. So quantum also is important for the governments by themselves, because the government should help not only for the market, but also to help for the innovation. So we need to discover, we need to make patents, we need to make a lot of research in order to let the quantum advancing. As I mentioned, for example, here we have Japan. They have increasing to $10 billion in total. 73% have been increased for Japan. It's ranking #1 for the announcement of the public acceleration. We have USA for 5%, and we have Australia 6%, and Singapore 2%, and also Spain 9%, and others to 5% in total. This is according to the early 2025, the total public announcement. So Japan has been doing above 75% almost in the public investments. So public investment is needed in order to help a lot of engineers and stuff. So companies, there are many. According to the copyright here in 2026, the Soter Group Intelligence and Advisory, there are a lot of quantum computers nowadays, different nature of way how you construct your quantum processor unit. So as you can see here, the total number according recently is 89 quantum computer hardware companies, and most of them, they are working in using the superconducting quantum processor units up to 30. Then it could be the second rank is the silicon spin, and then it will go there into photonic, quantum computer, neutral atoms, trapped ions, and many others. As you know, we have IBM, we have Microsoft, we have a lot of startups in France as well. They are using different type of quantum processor units. So this is the general way how the people has to know where are we now in the hardware engineering and the number of startups. So OpenVQA Hub is our kind of foundation. We have created it since 2023, and I'm leading it, and we have a lot of advisors. Thanks to them, they help us how to shape and how to progressively adding more and more efforts in order to be the gate of attracting the talents, the engineers, the students globally in order to work in the quantum computing. So a lot of open sources also has been doing from IBM and Google and Microsoft. They are growing the ecosystem. So open source is highly encouraging. Like OpenAI, it's really was an open source, and then it has been attracting a lot, and now it's making market. So the open source always is a gate in order to go later into the competition for entering into startups and making a lot of market. So here we are, we have done a lot of progress since last year, and we have done a lot because OpenVQA, it's open variation quantum algorithms that can enable the students, the engineers, and the algorithmic developers making hackathons, making schools, making a lot of events in order to interact together, because interaction is very important. So the interaction once happen, then the innovation is growing further and further. Last year we have been in Vietnam, and it was a great experience for us. And this year is going to be in Thailand, which is going to be also a great experience, and it's a great event. We are going to make it in October. So we are looking for highly skilled researchers and highly skilled also professors who are going to be in a great moment, in a great place, a great avenue, in a paradise in Thailand this year. And we are really happy to discuss and announce it later. So open source quantum is very important, as I mentioned, because you can share knowledge, you can share open source tools, you can make global collaboration, and here we are. So very briefly, for those who wanted to know more technically of OpenVQA, we invite you to contact us in order to see how can you extend the algorithms, how can you add more methods in order to tackle precisely the electronic structure method in the molecules, in the atoms, in the crystals, and more into material designs, many applications also into quantum chemistry and quantum physics. So our game at the end is to go to real applications. So our roadmap is very clear. We wanted to now apply to real NISQ devices. So we have seen so far many early stage startups. They have starting to offer open sources, and we wanted to contact them soon in order to start to apply and in order to start to interact with them to make events and stuff. So our achievement this year was we have more and more members. They have been came to the community. We have been published alpha versions, alpha 1.0, alpha 1.1, 1.2, and the community is growing, as I mentioned. And soon we will go to the OpenNISQ platform in order to go further in the vision. So now I would like to take 1 minute in order to tell you what will happen for the next 1 hour and a half. First, the next 20 minutes, we are going to have a panel with special people from the world who are Professor Hicham El-Ulshi in the École Polytechnique University de France, Professor Rahul Mitra in India, Institute of Technology, Bombay. Myself, I'm going to moderate the session. So there will be 3 questions almost for each of the panelists. And we have Alex Khan, VP of Quantum R&D in BQB in USA, Professor Tian Q from Swinburne University of Technology in Australia, and Dr. Abdelhamid Al-Fattah, founder of Quantum Innovation Startup, and also Thurasan Madian from AI engineer from WYW Startup. And then we are going to have another session more into the OpenVQA with 2 nice engineers from the OpenVQA, Kishif Da and Shams Al-Arfin Niber, who are going to introduce us for 20 minutes the importance of OpenVQA and how to use it. Then we are going to have speakers from the OpenVQA community, Tahir Manzoor from the GP Institute of Engineering and Technology, Birawet Bowen from Imnots College in USA, Edmonds College, and he is from Thailand, and Ilmahdi Karim, he is available also in quantum drug discovery in France. So let's now go to the panel session. Again, good afternoon, everyone, and welcome to this special session for the World Quantum Day. Today we bring together researchers, professors, students, and industries, expertise to discuss the future of the quantum technology. So here we are. They are there to discuss the importance of the intersection of AI and quantum computing and how they could be important for the real world impact. So this panel is organized by WYW, Quantum Innovation, and the OpenVQA Hub. We will follow a structured discussion and with a short introduction from each of the panelists, followed by thematic questions and a rapid fire round in order to close the session. So let's begin with a very brief introduction. Please keep it under 1 minute, each of you. So to follow the flow, first with Professor Rahul Mitra, you please introduce yourself and your research first. Then Professor Tian, then Dr. Hicham, and then Dr. Alex Khan, and then Thurasan, and then Dr. Abdelhamid. So please, I give you the floor to speak. Introduce yourself in 1 minute, Professor Rahul Mitra.
Yeah, thanks, Dr. Haidar. My name is Rahul Mitra. I'm an associate professor at IIT Bombay in Mumbai, India. I am specifically trained in many-body quantum chemistry. And for the last 5 or 6 years, I have picked up quantum computing and trying to apply the quantum computing method for chemistry and related problems. Thank you.
Thank you. Professor Hicham.
Yeah, I am Professor Hicham El-Ash. I am chair of research on quantum information artificial intelligence at Université Polytechnique de France. Just I landed a few months ago in France, and then we are building a group for quantum machine learning. My my skills are combined between quantum optics or quantum information, quantum computing. And I have several patents in quantum technology and would like also to continue in this field. This is very nice one to see collaborators. I have advertised for four postdocs for quantum machine learning. Don't hesitate to contact me if one of you have these skills.
Fantastic. Thank you so much. I would love now to move to Dr. Tian Q, please.
Thank you. My name is Tian Q. I'm from Australia. It's midnight here, so good night or good evening to everyone. I've been interested in the foundation of quantums and quantum computation for some time. I'm particularly interested in adiabatic quantum computation, which has similar feature with the qubits and the Q-gates based quantum computation and VQE, and also for quantum annealing as well. So that is also I'm also interested in some other problems in the foundation of physics and also in AI in general. So that's me from Australia.
Thank you so much. Fantastic. We are going to go deeper into some questions for you later on in the panel. So I would love to move to Alex Khan, please.
Hi, everyone. I'm Alex Khan. I am a VP of Quantum R&D at BQP, which is a startup in CFD simulations using quantum solutions. My background has been in mechanical engineering, business, entrepreneurship, leading large teams, but I got into quantum computing in 2018, wrote papers on optimization, also eventually wrote a book, Quantum Computing Experimentation with Amazon Braket, to kind of show how quantum computers can be used by the industry. And I'm also a fellow at the University of Maryland National Quantum Laboratory, where we work with students, PhDs, in having their research done on IonQ or on the ion trap.
Excellent. Also, you are missing you are an advisor for us in OpenVQA Hub, so you have missed this point, but we are very happy to have you in the hub of OpenVQA. So now I would love to move to Dr. Abdul Hamid Al Fattah from Saudi Arabia. Please, Doctor. Dr. Abdul Hamid? Perhaps he is not with us today. Abdul Hamid, you hear us? Okay. Maybe I would love to now to move into Surasan, please. Please, Surasan, introduce yourself.
Yes. Hello, everyone. So my name is Mahadevan Sudarshan. I have a background, to present myself, I have a background in physics. I have a master's degree in physics and specialized in nanoscience and soft matter. And I am currently completing a second master in AI engineering. I am very passionate about, of course, quantum computing, and I wanted to know more about. That's why I joined the company of Dr. Mohamed Haidar at WIO as an AI engineer, and I hope that I can investigate more about AI systems applied for quantum computing.
Thank you so much. You are welcome to join the startup. And now let's move. Thank you all for these nice introductions. And I would love now to move into the discussion with a structured question across the quantum, across the AI integration with the quantum and the global ecosystem. So let's start with the first question to Professor Raoul Mitra. Let's focus on the quantum chemistry and variational quantum algorithms. Since we are Variational Quantum Algorithm Hub, so you are the first who can be addressing this question. You have been working on the electronic structure methods since 2008, and you have been published because we follow your Google Scholar. You are really doing a lot of work, and that's really amazing. And now you are focusing specifically on OpenVQ in the VQE. How do you see the future of variational quantum eigensolvers in quantum chemistry nowadays? Thanks.
Sorry. Yeah. Can you hear me now?
Yes, sure.
Yeah. Yeah. It's a good question. See, theoretically, it has a lot of promise for sure, because you have the variational bound and everything. So in principle, you can do a lot of things with the correct parameterization, correct expressibility of the answers. Where we are sort of lacking is one is that the math works, doesn't support. So here is the catch. So you need to integrate appropriate error mitigation techniques, because we are perhaps done with optimizing the circuit, at the answers level or at the circuitry level, that it can be done pretty well. But still, when you are going to take the quantum advantage, your hardware must support. And in order to make your hardware support, you must integrate it with proper error and error mitigation techniques, number one. And number two, the problem that I immediately see is the scalability, because I don't see that any of these architecture can give a very long coherence time for kind of the problem that matters for a realistic chemistry simulation. And we must develop what we call as the embedding techniques, that you embed the problem, you build up appropriate subsystem, appropriate fragments, and solve the problem by parts, kind of, without going into the brute force simulation of the overall system. With this,
Okay.
I believe that there is a lot of promise, theoretical promise. We must have AI and ML integration, and AI and ML driven error mitigation, and AI ML driven embed development of AI ML driven embedding framework that can take us a long way within the variational algorithms.
I see. So this is already answered the question to Surasan, because he's an AI engineer. I was going to ask him this question, but no worries, we will replace another shorter question. As a follow-up, Professor Olmetra, I would love to ask you, how do you think nowadays VQE can achieve a chemical accuracy at the scale, and as a hybrid approach? Do you think it will dominate the long term, or it will be stopping there at the NISQ era? Thanks a lot.
No, I mean, I believe that it will have its more advantage. I mean, we will be able to harness the quantum advantage in a long term, not in the short term. Because you see that the short term, you require additional circuit for error mitigation, which are always leads to a long, huge amount of quantum overheads. Okay, so we essentially will start losing the quantum advantage. But as we keep improving our hardware quality, I believe that for a more longish term usage, we will survive a lot.
Okay, I hope so, because I love this algorithm so much, and we are going to collaborate together a lot in the future. And let's dive more and more to make it applicable also, and at least it will be useful for the fault tolerant as well, in a nice way.
So because see that at a chemistry level or at a many-body level, those who are actually trained in quantum chemistry and similar condensed matter physics kind of a problem, we know how to solve the many-body problems. But the problem is that we must get proper support from the hardware.
Okay. Thank you so much for these brilliant answers. And I would love to move to adiabatic quantum computing now, to Professor Tian Ku. I would love to ask you, how can you compare the adiabatic approaches with the gate-based and the variational quantum algorithms in terms of power and scalability? How can you compare the adiabatic approaches with the gate-based and variational quantum algorithms? Thanks a lot.
Thank you. Yes. Quantum computing is different from the classical computing because we have more degrees of freedom, namely the superposition, the entanglement, the interference. And adiabatic quantum computation is a special paradigm within that quantum computing framework. And it's based on the adiabatic theorem, just like in quantum chemistry, where ground state is very important to be obtained. So we have a landscape, and adiabatic, normally classical annealing, we have to hop, thermal hop, but in quantum adiabatic quantum computation, we have tunneling and so on to move into the ground state. It is a continuous process. It's a physical process going to ground state to time. it can be digitized into the qubits and into the quantum gates
Yes.
to certain error that we can control by different time step. How to compare that with the quantum gate-based quantum computation? It is equivalent. There is a theorem with that, but in practice, the quantum gateway is now more advanced than the adiabatic. But also the adiabatic is also a different way to supplement that and open a new direction and very rich field to be delved into. The adiabatic quantum computation is just like a boiling frog. When you put a frog into a saucepan and then you turn up the heat very slowly and the frog will be boiled to death. So because the temperature is adjusted to the ground state, which is the surrounding bath. So it's also have some advantages. For example, with the qubit quantum gate-based computation, we need error correction. So we have many qubits, physical qubit to encode one logical qubit. For the adiabatic, it's more important about the gap between the ground state and the next excited state. And if that gap can be manufactured big enough, then we can have to a certain degree some of the error protection. But that hasn't been realized yet.
And do you believe that the adiabatic quantum computing would unlock the computational advantages beyond the current expectations?
In the longer term, because as I said, the quantum gate-based is now more advanced because that's more easy to implement in a way. For the continuous process of the adiabatic quantum, that's also have a lot of advantages. For example, we can use photonic quantum computation, where the qubit or the light subject to certain physical processes, and that may be an advantage. But a lot of theoretical work being carried out, but not many been implemented yet. It's share the same feature like quantum annealing, where we have a landscape and we try to tunnel into the lowest ground state, or also the VQE, which is a hybrid approach. And related to your previous question to Dr. Rahul, hybrid approach is also, I believe, is a long term. It's not just for VQE, but also for the long term of quantum computation as well, because quantum computation is a different way of looking at things, and it's complement and we'll need the support of the classical, the hybrid to advance forward. So not just in that particular VQE.
Okay, thank you so much for these insights, and I'm really happy to discuss further in the future about the adiabatic quantum computing and to see their power as well as scalability.
Yeah, particularly how it's connected to the VQE. That's something that hasn't been explored yet. Sorry, who's that?
Thank you so much, Professor. And I would love now to move to the quantum Saudi ecosystem to Professor Abdulhamid Al-Fattah. I heard that he's here back. Dr. Abdulhamid, do you hear us? Are you with us, Dr. Abdulhamid? Okay, so we need to move to another, no problem. I would love now to move to Professor Alex Khan. So on the occasion of the World Quantum Day, Alex, how do you see the evolution of quantum computing over the next few years, particularly for mission-critical applications? And what role do you believe BQB, your startup, will play in the ecosystem? Thanks a lot.
Yeah, definitely. Obviously, there's evolution happening in every area. So obviously, the hardware has to evolve. We are seeing larger number of qubits in quantum computers, the different modalities of quantum computers. We started out with annealers, superconducting qubits, neutral atoms, ion traps, and then very soon we will begin to see photonic systems. Quandela already has one available, and then PsiQuantum and others are working on it. I'm sure there's going to be other quantum, different kinds of quantum modality coming out. I think each one has their own advantages and can solve unique problems that are natural for that type of modality. The quantum algorithms obviously have to be improved. We have certain number of quantum algorithms that have proven quantum advantage or scaling, but when you
Hello?
Yeah, you are suddenly muted.
All right, somebody muted me. So on the algorithm side, we know the quantum algorithms that have an advantage, but on the other hand, there's data loading that has to also happen to bring your actual problem into the quantum computer. And sometimes we lose, or frequently we lose that quantum advantage in the process of data loading or taking a classical problem and converting it into a QUBO for an annealer. So I think all of these areas are being worked on every day. I see new papers, new methods, new techniques. And so the evolution is happening. And BQP is, as in BQP, I've got, various projects, and we are working in all of these different areas, looking at how to solve linear system of equations right now with algorithms, variational algorithms like VQLS, but then also how to continue to improve fault-tolerant quantum algorithms for linear solvers like HHL. We're working on physics-informed neural networks. So quantum versions of those, so quantum physics-informed neural networks and quantum physics-informed neural operators, which is a very interesting technology, and we've seen some advantages there. We're working on quantum Monte Carlo. I've seen advantages there and also been able to run those on quantum computers and see that they can actually produce results better than classical, even on the quantum hardware right now. So those are NISQ algorithms. And we're working on very Schrödingerization methods as well.
Nice. And another maybe a question, as we know that you have been working in the USA quantum ecosystem since long time. How do you compare it with Europe? How do you compare it with Canada? How do you compare it with Asia? Can you please give us a kind of perspective point of view? Thanks a lot.
This would be very my observation, because I've not been very closely associated with a lot of the ecosystems outside of the North America. I would say that Canada had an early start. I learned a lot from the Canadian ecosystem. They are ahead of the game. They've been in quantum machine learning. They have great teams over there. There's a lot of funding there. I think the US has obviously put in a lot of effort, funding, and of course, US has the scale. So with the universities and industry, I think the US is obviously, catching up and getting ahead very rapidly. I can't make any judgment call on the European ecosystem, but obviously I would say that every country and every region is attempting to get into quantum computing in their own way with their own resources. And I do believe that this is going to be a pivotal technology in the future. So, just like programming or just like computing, quantum computing is a fundamental technology that everyone should know, including AI. And quantum and AI definitely are playing a role together. So I was just noticing that Purdue University now requires all of their graduates to have at least an AI background. So I think that's a good start.
Thank you. And as a follow-up, where do you see the strongest acceleration happening today? Do you see it in Europe or in America or in China? How do you see, or Asia maybe, how do you feel it in terms of marketing and in terms of business as well?
I think that's hard to tell. Different countries are putting in a lot of money into quantum computing. I think the UK has also put in a lot of money. I don't know if I can make a good judgment on that.
Okay. Thank you, fantastic, Alex. And I would be really happy to focus more into what PQB doing in terms of using D-Wave and gate-based quantum computing. So I'm really happy to look further into details of that. Thank you, Alex. And I would love now to move into Professor Hisham Al-Ash. Professor Hisham, as you mentioned during the introduction, that you have now more than 20 patents, I would say, or 21 international, and you have been moving from Dubai very recently into France, into Polytechnique Hauts-de-France. Can you explain to us what, in general, because a lot of audiences now, they would love to know what a patent can represent in the quantum technology. Can you please define it and show the importance of having a value as a patent in quantum technology?
Okay. Let's begin with someone that we have done. For example, quantum memory. This is very important for quantum machine learning, for accelerating the calculation. Quantum memory is very, very important. And we have done one, and we have so now 3 patents about it. And that can accelerate all the calculation, the intermediate calculation you put there, and so on. That's one thing. Second thing, we have done also a nice patent about how you can cool the qubit without cooling the wires between. So this is, you take the superconductor quantum computer, you always put it in very low, what they call it, very low temperature, few fraction of Kelvin. So, and usually all the system, all the blocks of the quantum computer is refrigerated. And now suppose that you want to have to replace some qubits, to add some qubits. What you should do, you should take all the system from refrigerator and again work on it and return it. The idea now, that's what we have patented, is you could refrigerate the qubits independently of on the wires are in the room temperature without affecting the efficiency of the quantum computer. And this is means that if you have a quantum computer, you can have a quantum computer and you can add modules, and then you can extend it without the quantum computer obliged to be stopped and again fix it again. So that's one of the patents that we have done like 2 years ago or 1 year ago. By the way, we are trying to sell all our patents, but still in some process. I can tell you another one is that I'm using quantum graphene for quantum teleportation protocol. You can implement the quantum teleportation protocol by using graphene. Yeah, there's several others. That's one of them is more in quantum, I will say in quantum sensing or quantum technology, when you can transform a microwave to optical or optical to microwave through graphene. We have also developed some patent about soliton. Soliton is the way that to propagate without deforming their shape. Solitons on the we have done it in graphene. Yeah. Lately we have done the quantum blockchain. So we have proposed quantum blockchain, and we had in December 1 patent on it, and still some patents in the process for quantum blockchain. So let me stop here.
Amazing, Professor Hisham. This is really very nice, and we are proud to see all these achievements. Especially, this is encouraging for the innovation in this field to have patent in quantum technologies in different pillars, of course. I would love to ask you another question. People sometimes they speak about qudits, and some people speak about qubits. Do you have certain way, how can you mention, because you have been, I have seen your research recently and you have been working in the qubits over the qubits. So how can you differentiate between qudits and qubits? And what do you think is better in the future, to use qudits or qubits? Thanks a lot.
Okay, thank you. That's good to ask me about it. So, you know, the qubit, you can realize almost of the system that we are working is in quantum computer is qubits. Or all what we have, whatever, Google, Rigetti, all this guy, IBM, and so on, they are using qubits. A qubits is simply two-level system. If you have two-level system, 0 and 1, a combination of them, you have the qubit. And then when we speak about QDIT is multi-level system. Multi-level system, let's see again, for me, as I see it, is like a computer, classical computer, based on binary, 0 and 1, on DNA, based on 4, A, T, C, G. So who is powerful? The natural computer, this based on biology, or the binary? We know that we are much powerful calculation when we use the DNA. There's a lot of things to do. The same. If we go to the higher level, we have more opportunity to make more calculation. And in particular, this is what we have done, what we call it quanzistor. Well, that's just the invented word. This quanzistor, this is the basis of second generation of quantum computer. By the way, the people begin to do some experiment in it. We have begun like a few years ago by end 22, we have published it, but we have seen people begin to do experiment in four-level system, or I call it quanzistor. What is the particularity? The particularity is when you couple it to the symmetry. You see in the symmetry in physics, the symmetry is when you have conservation of energy, you have a symmetry, or you have conservation of translation or rotation, you have always symmetry. And these symmetries have good impact on physics. The same, if you have symmetry, you could be protected from classical noise on quantum noise. We have used some specific symmetry, what we call it omega symmetry. Is a little bit abstract algebra, but is in simply there is a rotation. Mainly is you can consider as rotation with 90 degrees, 180 to 170, and 2360 degrees. Okay. And with this system stable to this rotation, we have shown that the system is stable. We can stable against the fluctuation, classical on quantum. And if you return to the research in 2000, people speak about multi-level system as for quantum cryptography is much more stable than by using qubits. So that means two-level system or qubits, they are somehow more secure compared to multi-level system. So you can see that I think the next generation of quantum computer, or the next revolution of quantum computer, will be based on multi-level system. We call it QDIT in general. So that can do it when you have 3 and so on. Okay.
Okay, thank you. Very interesting to read more and more about these QDITs, and I'm very curious myself as well to know more about it. We can discuss about it more later, Professor Hisham. Thank you for this exciting talk. I would love to move now into the mix of AI and quantum through Surat Hassan. You are currently studying AI, Surat Hassan, in the AI Van City in Paris. How do you see artificial intelligence can help accelerate quantum computing? Just let the audiences know how the AI can help in quantum. Is very important, especially in the design of the algorithm, design of the circuit, design of the optimization. How can you describe it in few sentences? Thanks a lot.
Yes. As my understanding, right now, without AI, with AI, I will say further, it's way much better to use AI for computational cost and reduce the computational cost. And I know that in quantum, I would say algorithms, we are highly on the research on that. And there is some research actually that are made for about this bridge and these problematics. For example, Google DeepMind have published AlphaQubit. I don't know if you know it in Nature. It's a transformer-based neural network that learns to decode quantum errors on the surface code, and it was tested on real hardware. Data from Google Sycamore processor, and it outperformed every existing algorithmic decoder. precisely because it captures complex noise patterns like crosstalk and leakage that design algorithms struggle with. So there is some research that are made on that. There is also the Harvard team that I recently find out. I think that it's 2 days or yesterday that I see that they're introduced a convolutional CNN actually decoder that is called Cascade that reduce the quantum error rates. I think that by up to 70 times while being fast enough for real-time users. So yeah, there is some discoveries that are made with this bridge between AI and quantum.
Nice.
AI for quantum, yes.
Thank you so much. My last question for you, have you observed a real example where AI improves the error mitigation methods or improves the quantum framework, for example, or workflows? Have you seen that in reality, or have you seen some publications about that?
Yeah. But as I discussed just before, as I mentioned the alpha qubit that I talked just earlier.
It's existing as real, yeah.
Yeah. And of course, I would say the traditional quantum errors decoders use fixed rules, and they are fast, but they struggle with the messy, I would say, correlated noises.
Okay.
That real quantum hardware produce. But what Google DeepMind did was train a recurrent transformer that learns to decode directly from data. So
thank you. Yeah, if you don't mind, you
Yep.
can share us all these things. I would love to read
Of
more
course.
and to share the community by emails. Now, I would love to thank you so much, Surasan. My last question to Dr. Abdelhamid Al-Fattah. Are you with us, Doctor? Doctor? Okay. Apparently, he was missing
Yeah.
the point.
How are you?
Okay.
Thank you so much to
Doctor, you are
invite
very
me for
welcome.
this. Yes.
Yeah, so we have two questions for you very quickly. How do you see the future of quantum technology in the Saudi Arabia? First question.
Good question. Actually, first of all, I would just thank you for inviting me for this day, Quantum Day International, for this conversation. And for answering your question, the quantum in Saudi Arabia these days, it's really the people talk very highly because they need the transformation from the normal data to the novel technology like quantum and AI. So the government side and the private sector, they are really interesting in the quantum and AI. Yeah, this is the situation right now in Saudi Arabia regarding the quantum.
Okay, very nice, Dr. Abdelhamid. And why did you choose to establish a startup in quantum innovation in this field? I mean, especially you are an expert in communication. What makes you happy to really register a company, quantum innovation startup in Saudi Arabia? What was the reason? What was the motivation for you?
Yeah, the reason
Dr. Abdelhamid.
Yes.
Yes, doctor.
I met with the Minister of Communication before,
Nice.
and he talked very highly about the quantum technology in Saudi Arabia. Within 2 years, it will be booming. And I'm just asked friend around me, and they told me, you can go for quantum, for example, quantum innovation. And I registered that company, and now just establish it, and I'm doing some project with some people, and inshallah we will do very much successful for that.
Fantastic.
Yes.
Fantastic. Thank you, Dr. Abdelhamid, for these
Dr.
insightful
Abdelhamid.
answers. I would love now to conclude, and I would like to ask
somebody call me,
each.
Dr. Abdelhamid.
I don't know, but maybe there is some, I don't know. So to conclude, I would like to ask each of you one short question. In one sentence, we can start in the chronological order of the shared screen here, from Professor Hisham to Raoul, then to Alex, then to Professor Tian, then Abdelhamid and Surasan. What is the biggest opportunity in quantum technologies in the next 5 years? 20 to 30 seconds, each of you. Thanks a lot. Professor Hisham.
So A very good question. What is the opportunities? Means what is the potentiality of quantum computing?
What is the
And the
biggest one? Yeah.
Right, sorry?
What's the biggest opportunity in quantum that the people can see from the effect of quantum technology in the next 5 years?
First of all, this is acceleration of the calculation in general way. A problem of more of security threatening and security unsecure the data, because now it's if the quantum computer is here, the data is not secure. We go to quantum cryptography, post-quantum cryptography. This is a challenge and opportunity. Opportunity for sensing, ultra sensible sensing. Opportunity for calculation in science in general, on prediction, weather prediction, catastrophe prediction, or hurricane, and so on. In the finance that people use it, in the computation in general, with real time. That means, for example, optimization also. In flight now, if you take one flight, you are always late because of this optimization problem. And maybe in medical science also, improvement medical advance, medical advances and so on. I think 30 seconds is enough.
Yes, exactly. Thank you. Nice. I would love to see Professor Raoul what he thinks now about this question as well.
Yeah, so material science maybe perhaps, and that includes drug discovery and other allied fields, particularly in attacking some of the problems which are not solvable in classical hardware.
Okay, thank you. Myself, also, if I want to answer, I mix between both of you. I think it's in the quantum cryptography, it will play a big changing role, as Professor Hisham mentioned. And I think in the medicine and in drug discovery, it will play a big role as well, in the material design as well. But this, nevertheless, we have a lot of logistics, finance, also the banks, the energy systems as well, like CO2 capture and many others will play a role in the next 5 years. I would love to Alex, please. Alex, what do you think? What's your perspective about this question?
Yeah, of course. I mean, there's a lot of work going to happen in quantum cryptography, especially as quantum computers get stronger, and chemistry. Of course, I'm working in the linear solver area, so obviously I'm seeing a lot of movement in that direction. But I think it's important that we will start moving from variational algorithms to more of the actual high fidelity quantum computing algorithms like HHL that have a promised advantage. So I think there'll be a lot of research in that direction as people start shifting from just having variational algorithms working in current hardware to fault-tolerant regimes. Also, I think the photonic systems are very different, but I think there will be a lot of push towards photonic systems and the quantum network.
Okay, let's see. It's really very exciting to see what's going to happen. Professor Tian, please go ahead.
Yes. What started the the movement in the quantum computing investment was the cryptography, and now there was recently a paper that the number of qubits that can be used for the Shor algorithm has been reduced theoretically from 1 million to 10,000. So in the next 5 years, who knows, the advance in engineering may help that. But talk about the abaotic quantum computation and the variational one, they are very much suitable for optimization. And optimization is a big problem, important problem, and has been progressed through the financial portfolio optimization, the risk, the logistic, and that I think will be moving fast in the next 5 years. And beyond that, quantum chemistry and also the protein folding problem or the pharmaceutical, the drug discovery as well. That a little bit more difficult, but optimization is something that quantum computing can do very well, in particular with
Absolutely.
the adiabatic.
Okay, and on top of that, we miss the defense also because it will help a lot in the defense sector as well. I would love to move Dr. Abdelhamid. Dr. Abdelhamid, what do you think about this question?
Yeah, I think the revolution of the quantum technology these days, it's very high internationally. So it starts by quantum day, you see. And I really agree with all the people, they talk about quantum, rather in Saudi Arabia now and in this forum with you guys. I'm really yani, happy to hear about the future of the quantum.
Yeah, you mean like it will lead to more innovations, more interactions between
Exactly.
researchers and developers. Okay, thank
Yeah.
you. And Surath Hassan, would you like please to end this question by your vision? Thanks a lot.
Yes, so thank you. So for myself, I think that the big opportunity in the next few years is actually about more interpretability. Why I say that? Because making quantum and AI systems understandable and trustworthy is fundamental. Because we want to, of course, work on very sensitive areas like healthcare, finance, or defense. And we already found, for the moment, we already trouble with, I would say, deep learning models because they are black box models, even if we have some mechanistic interpretability stuff that we can use. But for quantum circuits, I would say it will be much harder to understand it. I would say, I say for common people, and work on this interpretability things. I think it will be very useful, and of course it will be like something of course very important for the next few
Fantastic,
years.
fantastic. Thanks a lot. Thank you to all our speakers and participants for this inspiring panel discussion on the World Quantum Day 2026. I hope next year we will have another panel more exciting as well as this year, and it will be inviting you again, and I hope you will be available. And today we explored quantum computing from theory and AI algorithms and industrial applications. Next year, 2027, we see what's going to happen. Maybe smart algorithm can change all the game, as Alex mentioned, or maybe we will have a lot of some new discoveries, like also as Surasan mentioned, we have maybe new way AI will help us. So we really need to mix AI and the quantum in many different applications. So thank you a lot, professors and engineers, for joining us in this panel. Now I would love to move into a great two speakers, engineers who has been working super hard in the OpenVQA package. In the software part, programming, Kishtif Dav and Shamas El Arfin Nibber. Please, Dav, go ahead, and now it's your 15, maybe 10 minutes maximum for you to present your slides, and then Shamas. And afterwards, we move to three speakers from the India, USA, and France, Il Mahdi Karim, in order to speak about their contribution. And then we announce the two winners this year who has been working super hard in OpenVQA. Thanks a lot. Go ahead, Dav.
Okay. Thank you, Professor. Let me share my screen. So let me introduce myself. My name is Kshitij Dave. I'm from India, completed my master's in physics, and mainly I've been working in the open source of developing new OpenVQA algorithms and integrated with the GitHub and making a unified backend through it. So yeah, let's. Can you see my screen?
Yes.
Yes.
Yes. Yes.
Okay, yeah. So I'll be presenting one of the, we have actually integrated two of the algorithms. One is VQE and QAOA. and I'll be presenting the QAOA workflow. First, I will explain how it works and how I integrated into the GitHub workflow as part of the OpenVQA. So QAOA is a special kind of VQE where the unsarts are repetition of two Hamiltonians. So it will form a repetition which actually search the subspace of the Hilbert space, and these unsarts become the two design. Yeah, so this unsarts become two design when the depth of the quantum unsarts when the depth becomes too big, and there are many it has been said that the QAOA is with the infinite number of depth which it increases, it replicates the adiabatic processes. So this is how we actually implement the adiabatic as per onto the gate-based system. So we have similar to any workflow of variational quantum algorithm, we have classical optimizers which basically used to optimize the parameter of the unsarts. The quantum circuit is used to calculate the expectation value. And here we have introduced one layer of OpenVQA integration. What it does is it selects the backend and the hardware backend with the different quantum circuits with the different languages. So we have included language from Qiskit, we have included PennyLane, we have included Cirq library, and you can integrate different libraries from their template-based structure, and we have made one unified platform through it. I will go next to it. So this is one of the key things, key results that we have also showed in the alpha version about the QAOA, how a system evolves with the energy and with the number of iterations, how the circuit depth creates performs the better. So, and it is not mandatory that every time if we increase the circuit depth, it should perform the better. Theoretically, it should, but experimentally, this is not an result that we expect to see every time. We have also included reproducibility in one of the key features in the OpenVQA, where you can just use seed in itself a simulator, and basically you can reproduce the same results and store your results every time, so you don't have to worry about that. All the hyperparameters and construction can be controlled through the OpenVQA backend itself. So there is a backend abstraction layer which is called BAL, and which controls everything. So you can choose your optimizer as per your requirement. You can see the convergence as per the problem statement itself. Yeah, there is always a bottleneck in the variational algorithms, particularly when you have when you talk about the subspaces on the from the Hilbert space. So for example, here is sorry. Yeah. So for example, in QAOA algorithm, the barren plateau is one of the thing that it is very common problem, because of the as the number of dimension of the generator of the unsarts, as it becomes scaled largely, the it becomes very the harder to scale it, and the convergence can become like it can drop, it cannot drop, or maybe it becomes stagnant to some cases because of that. So this actually we have put one of the part in our simulator, which is it can detect itself whether the barren plateau will occur or not. So this is one of the features that we have also added. Um, we have found that yeah, the choice of optimizer is always a critical in this part, as the and the other professors have mentioned, the scalability is one of the issues. um, and the depth versus trainability is also basically integrated, as in one of the, I think, Jupyter Notebook, we have given a tutorial about the depth versus trainability. So how the trade-off and the cost of optimization landscape becomes harder to navigate, and how the difficulty becomes imparable with that.
Okay, fantastic, Dav.
Yeah,
You
I think
already started to, yes, please. Thanks a
yeah,
lot.
yeah, just one more slide I have, which is in general way how OpenVQA works, the architecture wise I have mentioned here. So a user have its own problem statement, which it can either write it in the Qiskit, or it write it in Circ or any way, or it can also take the template based upon uh, these uh, these languages. Then OpenVQA is an platform which aggregate these things. So it aggregates every circuits and onto the platform, and you just have to mention uh, for any problem statement, you just have to mention the hyperparameters. For example, with classical algorithm do you want to solve this problem? Um, what optimizer do you want to use it? What do you want to put seeds into this, or you want to replicate the results or not? After this, this goes to the backend abstraction layer, where everything is translated and like used in a simulator, which is also developed by the OpenVQA itself. And after that, it will go through the hybrid workflow loop, and it will work. So it is an platform that integrates multiple languages and multiple circuits into one platform as of now. Yeah, last our next target is to integrate more backends into it, make a we haven't included any hardware as per now, but we are working on to the different hardware. When the hardware comes, the error part is always been there. So yeah, error mitigation techniques and the techniques which are already there, we will also include it along with the different newer algorithms. This is one of our part now. Yeah, so these are some of the limitations that we want to achieve within the next 6 to 8 months. We will complete these things.
Fantastic.
And we are also like we are also inviting many students or researchers. Please contribute, please commit to our GitHub repo and be a part of it. I think that would be really great to see that the contribution of many peoples and many students and researchers in this domain. Yeah, thank you.
Excellent. Thank you so much, Dav, for this insightful discussion about OpenVQA, more technically about the GitHub, how many stars we already have so far, how many people we already have so far, and how much involvement. So thanks a lot. I would love now to move to our next speaker, Shamas Din Al-Arfin, in order to present us in 10 minutes your work, and thanks a lot for the discussion.
Hello, am I audible?
Yes, sure.
Okay, let me share my screen. Yeah, can you see my screen, everyone?
Yes, sure.
Okay, okay. So good evening, everyone, and to my respected panelists, researchers, and my fellow engineers and everyone. And I am Shams ul Arifin Nabir. I'm based on Bangladesh, and today I will present my work about OpenVQA. And of course, it's a pleasure, it's an honor for me to present in this World Quantum Day 2026. And yeah, I will talk about the problems we have solved in this package OpenVQA. So I will go through each of the problems that we aim to fix or already fixed in our OpenVQA package. So the problems we have today in the quantum SDKs are mainly the fragmented ecosystem and the high barrier to entry, and also the backend lock-in, excessive boilerplate, and opaque architecture. I'll go through each of them and I will tell you why these problems are very, very critical in this situation. So the fragmented ecosystem means it has like we have a lot of like frameworks nowadays, like IBM, Qiskit, Penland, Michael, right? So we have to focus on like for each problem for like we have to focus, we have to know these three like, or there are more maybe for the frameworks, but in this package we try to solve this issue of frameworks where we don't need to learn all the frameworks. We just need to know how to use the OpenVQ, and all these frameworks are really integrated into our package. So it's very, very interesting. And the high barrier to entry. So the steep learning curve for the beginners, it's very hard for the beginners to learn all the course, and we try to make it very organized way for the quantum computing learners, and also the researchers will come to the research part, how research will be benefited by this package. And also we have backends locked in. We just have to just select the backends, and boom, we can use the backends very easily. And we have like too much repetitive set of code, the cluttered research workflow. So that's the problem we are facing for the other frameworks that we have. But for ours, we don't have to just do the repetitive codes. We have all circuit setups, answer setups, and also like the Hamiltonians and the functions we have already set it up in the package. And lastly, the architecture of the other libraries, or I would say the frameworks, are really vague in terms of like structures and deeper learning and contributions. So ours is kind of easier than the frameworks that we built. And my co-engineer already explained it, what is OpenVQA, but I'll just give you an easier explanation of we just tried to like unify the APIs of major NISQ algorithms, and then we added the backends that we have already present from IBM, Qiskit, and Penland, blah blah blah. And also it's very beginner friendly, and also ResearchGate architecture. It has a design for various algorithmic research. My co-engineer they've already talked about QAOA, and I will maybe cover up the VQE part. So let's talk about the VQE part. And it's actually a quantum classical algorithm. It's not a classical algorithm, to be honest. And it already many of the professors talk about VQE in this session, and they gave a very good explanation of how it works and everything. But I will give you clear explanation of how we use this VQE algorithm into our package, and how it can be used and stuff like that. So it actually doesn't hinders the classical methods, but it actually complements them, to be honest. And it's I believe it's long-term suggestions in terms of the quantum classical methods. And so in our package, let's talk about a little bit about how VQE works. So VQE is basically works in preparing the unsudge, and also measuring the energy, ground state energy, and the classical optimization for COVILA, SPSA, and it repeats itself until it converges. So it's an interesting method. And also the real world application of the VQA, we have quantum chemistry, of course, and we have drug discovery, battery technology, we have material science, nitrogen fixation, nuclear physics. I will go through each of them because it's very important thing for quantum chemistry nowadays to compute ground state energies of all molecules and predicting the bond lengths, reaction energies, and activation barriers with quantum accuracy. It's very crucial for quantum chemistry, in fact, and also the drug discovery, protein, and also for the simulating molecular interactions for pharmaceutical design, identifying the candidate molecule that bind to disease targets more efficiently. So this drug discovery domain is very much like dependent on the VQE part also, and also like the battery technology. We have lithium-ion cathode batteries, which are model of electrode materials in at quantum level to design higher capacity and faster charging batteries for EVs and grid storage. And we have like material science. We can discover new superconductors and also magnetic materials and catalysts for solving correlated electron systems. And we have also nitrogen fixation to simulate nitrogen fixation engine to design more efficient fertilizer catalyst, and also to compute nuclear binding energies and study fundamental interactions in atomic level. It's very crucial for also nuclear physics. So ansatz, so it's very important for the VQE to design ansatz and Hamiltonian. And in our package, it's very clear. We have very clear ansatz design and Hamiltonians, and we have optimized for NICS devices. We are trying to optimize it, and it uses actually native 2-qubit gates with shallow depth, minimize noise impact, and also the UC-CST and symmetry preserving and such, and adaptive. It's very adaptive, in fact. And also for the Hamiltonian designs, we have polystring Hamiltonian, molecular Hamiltonians, and TF-IM model, and also custom Hamiltonians we can build with our package. And also, I have already talked about some of the features, but here are some of them. My co-engineer talked about QAOA. I am talking about the VQE, and in future we will be adding more and more algorithms. And we can also build custom ansatz and also multiple optimizers. We already have multiple optimizers, and we will be adding. Right now, we have Cobira and also Niger-Mead and SPSA Atom methods. And we are focusing on online execution to run an entire full VQA experiment with a single command result and OpenVQA at OpenVQA, and multi-framework support, as I already mentioned. And at next, who can use OpenVQA? My fellow engineer already talked about it. Who can use OpenVQA? So current limitations are not. It's not production ready, but we are working on it. We are at the alpha 1 version, and in the next version, I believe we can prepare for the use for the researchers and also for the students or the learners who wants to learn VQA and experiment with them. And limited backend coverage we have right now, like MyQLM, PennyLand, and Qiskit, and later we're aiming to add more and more backends. And basic Hamiltonian we have like basic H2 we have Hamiltonian supports, but later on we are hoping to add more and more Hamiltonian supports. And the performance currently not optimized, but we are currently working on it. And also for the real world execution, we will be because it's in software level right now, not in the real world hardware execution level. So we will be working on it later on. And here are the reference. And thank you so much for giving me the opportunity to present. Thank you all.
Thank you so much, Shamas and Dav, for being involved in this in contribution of OpenVQA. It's not an easy package. It's really not an easy job, but you make it simple. You make it clear and you make it ready for the beginners, you make it ready for the intermediate, and you make it ready for the experts. So that's why you layered it into beta, alpha 1, alpha 2, alpha 3 into alpha 4. And soon we will push alpha 1.2 and alpha 2.0. And this is already a great achievement. And I really would like to have more people to go with us into deeper detail with the project. Now, I would love to go into more discussion with new members of OpenVQA, who are 2 members only today, who are going to present and impress us by their work and their achievements. Let's see who they are. So we have Tahir Manzoor, and we have Pirawat Boon from Thailand and Tahir from India. We would love to start with Tahir. Please, Tahir, please go ahead, and you have around 5 minutes to talk about your work, achievements, and why OpenVQA is interesting for you. Then we move to Birawat. Thanks a lot.
Hi, hello.
Yes, we hear you.
Am I audible to you?
Yes, sure.
Okay, let me share my screen first. Yeah, is my screen visible to you?
Yes, sure.
Yeah, okay. Yeah, hi everyone. This is my pleasure that this platform is providing me the great opportunity to present my work. So my name is Tahir Manzoor and I'm actually from India. I have completed my PhD in mathematical sciences with applications to quantum dynamics. So in view of this World Quantum Day 2026, my presentation is about geometric algebra in quantum secure direct communications, or QSDC, or geometric algebra, which we also call as the Clifford algebra. So I'll start from like how everybody knows that how we represent the quantum states and how what is the geometric representation of quantum states in the entire this whole presentation, or this entire presentation. I am using the concept of like 2 things. One is a special product that we are using in geometric algebra that is known as a Clifford product, or sometimes we call that as a geometric product or Clifford product. And second thing is multivectors. Until now, everybody is aware about the vector, scalar, or there are some other different quantities which are analogs to vectors in the higher dimensions. Like we have bivectors in 2 dimensions. The geometrical representation for a bivector is like a rectangle, and we have a trivector which is like a cuboid, and other higher dimensional objects we have in the Clifford algebra or in the geometric algebra. So how we represent the qubits in view of or in terms of Clifford algebra? If we take like one Clifford algebra like CL30, where this 3 and 0, 3 basis elements, as we have some vector space, or even we have like this, we are usually using or we are frequently using Hilbert spaces. In Hilbert spaces, we have some basis vectors which help us to span that Hilbert space. Similarly, we have some vector spaces and all that. So this 3 and 0 in the subscript of the CL Clifford algebra, this means that 3 elements they scale to -1. When we take the square of those basis elements, as 3 elements scale to -1, and there are 0 elements which scales to +1. So a qubit is actually represented as an even grade multivector. We have 2 types of multivectors, like even grade and odd grade. It is simply like if we have like degree or the grade is their odd number or even number, so that represents whether we have the even multivector or even we have the odd multivector. So here we are using the even grade multivector, which is actually a spinor or a rotor. Rotor is simply this helps us to provide the rotations, or is used to interpret the rotations. in multi-vector state or in multi-vector, in terms of multi-vectors, we are using this notation like quantum state. Quantum state we are using in bracket notation, but here we are using this as some A0 plus AK Eij, where A0 is a scalar quantity and AK is a vector quantity, and Eij is some Levitas symbol. It depends on whether how many vectors, if they are like perpendicular, they will be like the angle between them, they will be 90 degree, and otherwise there will be orthogonal, orthonormality will be there. So then we have this block sphere. This is obviously known to everyone, like a state vector in on a block sphere from the CL30 that is represented by this sums vector S, and rotor operations, how we perform the operations by rotations, or how rotations help us to recognize the state. So any state which is like generated from ground state, that is given by a rotor. We have a rotation with respect to psi naught, and we have like this rotation. It is actually in terms of geometrical, this R is e power theta b by 2, where this b is a unit pi vector. This is a geometrically, this is a rectangle. The one vector will be in one direction and second will be in another direction, but they will form a rectangle. So this is the rotation. This is the representation of a rotation in terms of Clifford algebra. Then we have like these density matrices as basis elements. Usually what we are doing in the density matrices, we are taking some like coefficients, or we are taking some matrices. Here in terms of Clifford algebra, we are taking the basis elements of the corresponding Clifford geometric algebra. If we take the case of above CL30 Clifford algebra, we will take the basis elements, like we will take, there will be some scalars, there will be some vectors, there will be some bivectors. Actually, the total dimensions in CL30, that will be 2 power 3, means 8 dimensions. So there will be the last element which we call as a pseudo scalar, and element which is penultimate, last but one, that is known as a pseudo vector. So pseudo scalars and pseudo vectors, they are generated by the basis elements in the Clifford algebra. So here in a density matrix, we are, for a single qubit, density operator is represented by like this rho, which is 1 divided by 2 plus into 1 plus something and something, where these E1, E2, E3, these are our orthonormal basis vectors of the corresponding Clifford algebra. And this Sk, these are actually the real components of our block vector. Then this, what happens with this representation, this actually eliminates the need for complex valued matrices. So there is no need to have complex valued matrices. We can take the real matrices as well in terms of Clifford algebra. Then we have like gate operations in Clifford algebra. This is my next slide. How quantum gates are represented in terms of geometric rotations, or how geometric rotations are helpful to represent the quantum gates. Like we have taken gate poly X gate, poly Z gate, and Hadamard gate, and how are the operator, how an operator is representing poly X, poly Z, or Hadamard gate. They are given in this slide, like here in this table, operator in CL30. For X, there will be E1 basis vector, there will be E3, Z gate will be rotated by E3, and Hadamard will be represented by, this will be rotated by 1 by square root 2 E1 plus E3. And geometry action will be here, there will be a rotation of 180 degree or pi, and here will be again pi, here will be a reflection. Here will be no rotation for Hadamard gate, but here will be a reflection case. Then this is a circuit simulation, like if we have this state psi, we are using X, H, Z, we get R rotations with respect to psi state. Then we have skewer entanglement and the correlation. In geometric algebra, geometric entanglement is there, like in quantum secure direct communication, secure transmission that relies on correlation of base elements between like Alice and Bob case. If we have 2 qubit bases, then element is in, for a 2 qubit base, we will take the tensor product between CL30 and CL30. If we have a qubit case, there will be CL30 3 times the tensor product between CL30 and again CL30. Now, how this helps us in eavesdropping detection, as Eves interaction is modeled as a projection. In P, this is not a rotation or reflection or rejection, but this is a projection, eavesdropping detection. In geometric algebra, a projection onto a subspace, which actually reduces the grade of a multivector. If, for example, in case we have a multivector of grade 5 or 10, when we use this geometric algebra, this projection, case of projection, which is helpful in eavesdropping detection, this actually reduces the grade of the multivector, and which is mathematically detectable. So this makes more chances available to us, so we can detect the eavesdropper by using the Clifford algebra case. Now this is our entanglement circuit we have taken here as a dull state. So, and now algebraic framework for error correction. How algebra is used, how Clifford algebra is used in error correction or in the modeling of error correction. We have stabilizer codes in Clifford basis, as Clifford algebra provides this actually is a natural language for error correction in secure channels. Then we have this kind of syndrome detection. If in standard quantum mechanics, we measure like eigenvalues, in geometric algebra, we check the commutativity of the error multivector. There will be a multivector which is used wholly and solely for error detection. In that, in geometric algebra case, we take the commutativity case. For example, if in a multivector we have like two vectors like A and B, we will take their commutativity in terms of addition or in terms of multiplication. A B equal to B or A plus B equal to B plus A. So here we check the commutativity of the error multivector with the stabilizer multivector. So we will take two multivectors. One is error multivector and second one is stabilizer multivector. Then we'll check the commutativity in these two vectors. Then errors, they are represented like here I am using the symbol or letter E, which are actually the basis vectors. Errors are represented by basis vectors, and errors, E stands for errors. If EK anti-commutates with the stabilizer, then an error is flagged off. So this is error detection simulation, like we have data, then we have error here, and these are like C0, C0, and there is measurement. Then computational efficiency and security proofs, how the scaling and performance is being performed by geometric algebra. Geometric algebra actually this approach offers significant.
Excuse me, dear Tahir, you have one more slide to present because we need to move to the other speaker before the deadline. Thanks a lot.
Okay, I will conclude this. So there will be no matrix exponentiation, as rotations are performed directly by the geometric products, which is actually the sum of inner product as well as the sum of the exterior product or the wedge product. Then we have scalar mapping. The trace of some row A is simply the scalar part of the multivector. Then reduced latency case is there. This is essential for direct communication, where bit rates must be high and security checks are frequent. So these are the references. And if you have any questions, comments, you are more welcome.
Thank you so much, Tahir. Please, if someone would like to connect with Dr. Tahir in the future, please don't hesitate. This is his email, and he is more than happy to answer you the questions. Tahir is one of our bedrock in OpenVQA in the mathematical side, because he helped us a lot in mathematics. Thanks a lot, Tahir, for this brilliant session, and I would love to connect with you in the future. Let's now move into brilliant and talented student from Thailand and Edmond College in USA, Birawat. Please go ahead and I'm happy to hear your talk. Thanks a lot.
Yeah,
I met you
hello.
in Vietnam, right? Yeah.
Yeah. Good morning from Seattle.
Good morning.
Okay, I'm gonna be to share the screen right now. Yeah, for my part, it felt like a short, approximately 2 minutes, something like that. Did you see my screen right now yet?
Yes, we saw it.
Oh, okay. Yeah. Hello everyone again. Pilavit. Yeah, I came from Edmond College. Okay, I'm gonna be to tell you that what is the kind of achievement that I attended or that I got, yeah, from the United States. In the first one, I attended to the quantum hackathon at the MIT. I recognize that it really and really fascinating feeling when I working with my colleagues who come from different institutions for the problem that characterization that relate about the entanglement and the tomography problem, something like that. I know that is a really great experience to me, and I really love to share with you all that the United States can able to offer valuable opportunity in many and many ways. Alternatively, I'm also admitted to the quantum hackathon at the Yale University, and I am looking forward, to work with someone, in the beginning of the April 2026, something like that. Okay. And specifically on my research working, I'm also interested on the fixed point theory and the quantum information science. But on the first question that I'm going to be to answer that relate about the geometric interpretation of the fixed point theory, that little bit of the quantum information science, something like that. I'm going to be to reshape the field of the pure fixed point theory and the connection between the fixed point theory and the quantum information science theory, something like that. And I would like to be visualize them to the geometric interpretation and try to find the alternative way for application in variety way, something like that. Yeah. Okay. And this kind of work I had already to present them in the Shanghai, China, but now it's just a working process step. For that, I'm looking forward to collaboration and try to discussion on the fixed point theory or the opportunity in the quantum education around the world. And in the lastly, happy World Quantum Day. Yeah, wishing all everyone happiness throughout the year about the quantum mechanics and about the quantum computing. Thank you so much, everyone.
Fantastic. Thank you so much. I'm really proud to see what you have done and what you are going to do. And you are welcome to be a member of OpenVQA, and we would love to work with you more. By the way, I would love you to invite you to be in Thailand with us this year in the summer school. And we are planning to invite 30 top talented students in Thailand in a very fantastic paradise place. And you could be there because you are doing a lot of achievements. If your article has been published, you let me know, so we will invite you as a fellowship also to Thailand. Thanks a lot, and congratulations for your work.
Thank you. I appreciate that.
Thank you. Before we end, I would love now to move into the last stage, which is the announcement of the winners of the Open VQA Hub community. So as you know, we have more than 45 students, engineers in the community. And I don't know, each year I presented winners from the community because I would love to give them more and more enthusiasm for the next year, 2027, and the after 2028. It's more meaning more than just a kind of value of prize, but of course it's a prize as well. But it's just kind of to help them to encourage more people to come and to be there. So last year that we have 3 winners last year, but this year we choose 1 winner. But at the end, we were only able to, with a jury, we were able only to choose 2 at the end, both this year. So this year, the first winner, really, we need to congratulate him or her a lot because of her work, a lot, because every day, every night, all the assistants, all the organizations has been doing with a great efforts. A lot of time has been invested in the project of OpenVQA, in pushing, in talking with people, communicating, preparing posters. So this is something highly valuable because he put a lot of energy there. So I really wanted to thank Shams Al-Arfin Niber from Bangladesh because really, he does a lot of job. So great congratulations from the deep heart of, as a lead of OpenVQA, I want to congratulate you for winning the first prize of the World Quantum Day of OpenVQA Hub. Congratulations, Shamas. A great job and bravo, bravo, bravo. Please clap for him. And now for the second winner, also has done a lot of advancement in the technical part of the GitHub of OpenVQA, because has been publishing, releasing as well. So also Dav from India has done a lot of work. Everybody knows that. So congratulations for you, Dav, for winning also the World Quantum Day OpenVQA Hub 2026. So I am going to publish this in the newsletters very soon also, to let both of you more and more well known in the world, and to really everybody knows about your hard job and about your work. Thanks a lot, and congratulations. So before we end, I would love to thank again all the panelists for being with us, answering brilliant questions, brilliant answers as well, very valuable. We wish to have you next year, and let's advance from now until 2027, 14 of April, all the work and more people to come in the community and more people to present as well. Happy World Quantum Day for everyone, and please don't hesitate to reach us in the joining the community. Thanks a lot, and have a nice evening and have a nice day in USA. Thanks a lot. Bye.
Bye. Thank you.
Thank you. Goodbye then.
Bye bye, Professor. Bye, everyone. Congratulations for Dav and Shamas. Bye. اوكي ربحوا داف وشامس اخر شيء كيفين